Hello, welcome to the solving problems for the special limits. Looks like we have used the first 4 special limits, and I will solve problems. Example 7, that's the special limit number 5. That's the limit of cubic root of 1 plus x over 2 value minus the cubic root of 1 plus x value. Everything is over x. X goes to 0. This is 0 over 0 indeterminate form, and you can see it has a power, the polynomial, the power nature. It's probably the special limit number 5, which is also 0 over 0 indeterminate form. So I will try to reduce it to the special limit number 5. It's equal to the limit x goes to 0. I can use the radical. I can convert it into the power as 1 plus x over 2 power 1/3. As you can see, I'm trying to be consistent with the special number 5. Minus 1 plus x, also the same, power 1/3. Everything is over x. It's equal to. Now, the special number 5 is 1x power minus 1. I don't have minus 1. So I will subtract 1 and add 1. This way my value will be preserved. I'm trying to be consistent with the special number 5. So it's limit 1 plus x over 2 power 1/3 minus 1 minus 1 plus x power 1/3 plus 1. So you can see I just added and subtracted 1. Nothing's changed. Over x when x goes to 0. Now let me separate the expression inside of the limit into 2 fractions, which is equal to the limit of the 2 fractions. 1 plus x over 2 power 1/3 minus 1 over x minus. So I'm pulling this minus up front of the second fraction. This plus will change to also minus. So minus 1 plus x power 1/3 minus 1 over x. I hope that's clear. This minus is up front, so minus this one with a plus. Back to this plus. So that's the limit of the difference of the 2 fractions. Yeah, I just said the limit of the difference of 2 fractions. Since those are continuous functions, in this case, I can distribute my limit between each term. So the limit of the difference would be equal to the difference of the limits. So which is equal, I can write it equal the limit x goes to 0, 1 plus x over 2 power 1/3 minus 1 over x minus the second limit, the same x goes to 0, 1 plus x power 1/3 minus 1 over x. And you can see I'm very close, almost there, especially number 5, which says 1 plus the variable alpha minus 1 divided by the same variable. It's x over 2, so I need to divide it by the same x over 2 according to that limit. So if I divide by x over 2, I need to compensate the 2 by multiplying 2 here, just the constant. And what I have inside, it's exactly special limit number 5. That's number 5, and it's equal, it approaches to 1/3. This whole thing approaches to the constant, the power alpha, which is 1/3. And minus the second limit, that's exactly number 5. This whole thing approaches to also 1/3. Yeah, that's number 5. So it's equal to, and this 2, you can pull it up from the constant, up from the limit, so it will be 1 over 2. 2 is in the denominator, so it's 1 actually over 2. So it's equal to 1 over 2 multiplied by 1/3 minus this 1/3. So it's 1 over 6 minus 1/3, which is minus 1 over 6. And that's the answer. I hope that's clear. So that was the polynomial nature limit. I transformed it to the special limit number 5. And I resolved that indeterminate form. The last problem, example 8, I will solve it by using a combination of the previous special limits. We'll just practice. First of all, what's inside? What kind of indeterminate form we have here? 2x, 3x, 4x over 3, 1 over x power x goes to 0. So when x goes to 0, this goes 1 plus 1 plus 1 over 3, 3 over 3, 1, 2, 1 over infinity. So it's 1 to the power of infinity indeterminate form. That's the problem. How to resolve it? That's especially limit number 2. It helps us to resolve those indeterminate forms, 1 to the infinity. So I will try to convert it to the special limit number 2, which is equal to the limit x goes to, look at the structure, this is 1 plus the value. So I don't have 1 there. So let me just add 1 and subtract 1, and then we'll look at the x later, at the dynamics of x later. So it's actually 1 plus this fraction to x, 3x, 4x over 3, and minus 1, and power 1 over x. So 1 minus 1, nothing's changed. I just added, subtracted 1, made it kind of more messier, but it really looks like the special limit number 2. 1 plus, what is that? This value approaches to 0. So I need infinitely small contracted value added to 1. So x goes to 0. Now it looks very similar to the structure. But my power is 1 over x now. So it's equal to, according to the limit, the power is supposed to be the reciprocal of that infinitely small value, which is a new line. So it's equal to the limit 1 plus x goes to 0, 2x plus 3x plus 4 power x over 3 minus 1. I can bring minus 1 as minus 3 in the numerator. Yeah, bringing minus 1 into here under one fraction, so 3 over 3, so it's minus 3, and it's all one fraction, and this whole fraction approaches to 0. This is what I want according to the special number 2. Now I need to raise it again according to the special limit number 2. I need to raise it to the reciprocal of that infinitely small value, which is 3 over 2x plus 3x plus 4x minus 3. Yeah, but this power was not there. Now I need to compensate it. It gets messier. So multiply by the reciprocal. 3x, 4x minus 3 over 3. A lot of nesting here. I'm compensating this power, but I need that power. Why? I want to be consistent with the special limit number 2. And finally, the original power is 1 over x. That's the original power, 1 over x. Now what's inside? What is that value? That's exactly my number e. The special limit number 2, that value exactly approaches to e. 1 plus infinitely small, power of the reciprocal infinitely small. That gives me e when x goes to 0. Everything goes to 0. So finally, it will be equal to the limit of e to the power 2x plus 3x plus 4x minus 3 over 3. And 1 over x. So I can bring it as the product 3 by x in the denominator, and that's the limit of this e function when x goes to 0. So I hope that's clear. With power raised to another power, that's the power rule, you just multiply them, yeah? Multiply the powers here, and that's the result. E to the power multiplication of those two fractions will be 3x in the denominator. So it's next line, and it's equal to, now since my e function is continuous function is a continuous function, then I can interchange the limit and the e, which is equal to the e to the power of the limit of that fraction, 2x plus 3x plus 4x minus 3 over 3x when x goes to 0. Now let me work out my power of e. Again, this is constant 3 is 1/3 multiplied by this whole fraction. I can pull it up front of my limit, this 1/3, yeah? It's a constant, does not depend on x. So 1/3 up front of the limit multiplied by the limit. And here I have 2x, 3x, 4x minus 3 over 3. So I can split it into 3 fractions. This is 2x minus 3. It's minus 1, minus 1, minus 1 for each of those. I'm trying to be consistent with the special limit number 4 here. So minus 1 over x plus 3x minus 1 over x plus 4x minus 1 over x. And that's the limit of this sum of the 3 fractions. I hope this algebra is clear. I just separated one fraction into those 3 fractions this way. Minus 3, minus 1 here, minus 1 here, and minus 1 here. So 2x minus 1, 3x minus 1, 4x minus 1, and everything is divided by x by x by x. Common denominator, and 1/3 up front. I hope that's clear. And what is that? What do we have here inside? That's exactly number 4, special 4. That's exactly number 4. That's exactly special limit number 4, and they are all approaching to ln of the base to ln2, ln3, ln4. So this goes to ln2, this goes to ln3, and this goes to ln4. So finally, my answer will be e to the power of 1/3, and the actual limit x goes to 0. 1/3 and ln2, let me write it, ln2 plus ln3 plus ln4, and that is the basic property of the logarithms. The sum of the logs, the same base of e, is equal to the log of the product. You all know that. So it's equal to the e power 1/3, and inside here will be ln of the product 2 by 3 by 4, which is ln of 24. And it's equal to, again, basic property log. E power ln 24 is just 24 power 1/3, which is equal to the cubic root of 24. That's the answer. So when solving this limit, I was manipulating a couple of special limits, such as the special limit number 2 and the special limit number 4. This is what happens when you resolve indeterminate forms. Sometimes you need to manipulate many limits. And actually, I just covered all 5 special limits of the classical calculus. Only those are 5 special limits because they cover all the groups of elementary functions. The group of trig functions, the group of log functions, the group of exponential functions, and the group of polynomial power functions. And that's all. This is all the elementary functions known in the classical calculus. The gamma function, the beta function, the Bessel's function of the first kind, of the second kind, the integral sign, the integral cosine, those are not elementary functions. All the groups are represented by those limits. That's why those are called the 5 special limits. And moreover, those special limits help us to calculate exactly the derivatives of all of those groups of elementary functions. You know, the derivative is the limit of the difference ratio. When you apply number 3 to the log function, you'll get the limit of the difference ratio of the log function, and you'll be able to calculate its derivative. When you apply number 4 to the exponential function, when you apply the limit of the difference ratio to the exponential function, you will get this structure, and you'll be able to calculate the derivative of the exponential function. The same thing, number 5. When you apply the limit of the difference ratio to the polynomial, the power function, you'll get this form, and you'll be able to resolve that indeterminate form and find the derivative of the power, the polynomial function. The number 2, that is the discovery of the magical number e, and the special limit number 1, that is the limit of the trig functions. That's the last group of elementary functions. And again, the limit of 1 minus cosine x over x when x goes to 0 is equal to 0 is not a special limit. Is not a special. This is just a trig limit. This is just a trig limit. There are so many postings on the YouTube where people say that this is a special limit. No, this is not a special limit. This is just a trig limit because, again, I have to say that again, it is derived, it is reducible to the special limit number 1, and it doesn't have any new, doesn't carry any new information. It's still the same nature of the trig functions, doesn't give us anything new. All the 5 special limits are given here. They have new structure. They represent different classes of elementary functions, and they help us to calculate their derivatives. Again, the special limits help us to resolve indeterminate forms, but that's not the only way. You know, there are other ways to resolve indeterminate forms, such as the L'Hopital's rule, the way of factoring your rational functions, your polynomials. When you do that, factoring, reducing fractions, helps us to get rid of the indeterminate forms. Multiplying by the conjugate factor your numerator and denominator also helps us. This strategy helps us to get rid of the indeterminate form. So those are the techniques to resolve indeterminate forms, and also those special limits. I hope that was clear, informative, useful, and interesting, and I also hope you enjoyed that. I will see you soon. Thank you for your time. Have a nice day. Bye-bye.